Hi everyone, welcome back. In this Math 20-1 video, we are doing 20 worked examples on inequalities. We will solve linear and quadratic inequalities, decide solid or dashed boundaries, test points, and describe feasible regions. For y less than 2x plus 3, the boundary is y equals 2x plus 3. Since the inequality is strict, the boundary line is dashed. For y greater than or equal to negative x plus 1, the boundary is y equals negative x plus 1. Because the inequality includes equal to, the boundary line is solid. For y less than or equal to x plus 4, test the point 0, 0. 0 is less than or equal to 4, which is true, so shade the side containing the origin. Graph 2x plus y greater than 6. Rearrange to y greater than negative 2x plus 6. The boundary is dashed, and, because the inequality is greater than, shade above the line. Solve x squared minus 4 greater than 0. Factor as x minus 2 times x plus 2 greater than 0. The expression is positive outside the roots. So x is less than negative 2 or x is greater than 2. Solve x squared minus 4 less than or equal to 0. Since the parabola opens up, it is below or on the x-axis between the roots. The solution is negative 2 less than or equal to x less than or equal to 2. Solve x squared plus x minus 6 greater than 0. Factor as x plus 3 times x minus 2. The expression is positive outside the roots, so x is less than negative 3 or x is greater than 2. Solve negative x squared plus 4 greater than or equal to 0. This is equivalent to x squared minus 4 less than or equal to 0. Therefore, the solution is negative 2 less than or equal to x less than or equal to 2. Solve x minus 3 squared greater than 0. A square is always non-negative, and it equals 0 only at x equals 3. Therefore, the solution is all real numbers except x equals 3. Solve x squared plus 1 less than 0. Since x squared is always non-negative, x squared plus 1 is always positive. It can never be less than 0, so there is no solution. Solve x squared plus 1 greater than 0. Since x squared plus 1 is always positive for every real x, the solution is all real numbers. For y less than x squared minus 1, the boundary is y equals x squared minus 1. Because the inequality is strict, use a dashed parabola and shade below it. For y greater than or equal to negative x squared plus 4, draw the solid parabola y equals negative x squared plus 4 and shade above it. For y less than or equal to x squared minus 4, test 0, 0. 0 is less than or equal to negative 4, which is false, so do not shade the origin side. For the system y greater than or equal to x squared minus 4, and y less than or equal to 2, the feasible region is above the parabola and below the horizontal line. For y less than x plus 3 and y greater than x squared minus 1, the line is dashed and the parabola is solid. The feasible region is below the line and above the parabola. Find the intersection points of y equals x plus 2 and y equals x squared minus 4. Set them equal and solve x squared minus x minus 6 equals 0. The x values are 3 and negative 2. Write x less than negative 2 or x greater than 3 in interval notation. The answer is negative infinity to negative 2, union 3 to infinity, using parentheses because the endpoints are not included. Write negative 5 less than or equal to x less than or equal to 1 in interval notation. Because both endpoints are included, the answer is bracket negative 5, 1 bracket. A feasible region satisfies all inequalities in a system. For y greater than 0, x greater than 0, and y less than negative x plus 6, the feasible region is the triangle in the first quadrant below the line. Great work! For inequalities, identify the boundary, decide solid or dashed, test a point, and shade. For quadratic inequalities in one variable, factor, find roots, and test intervals. For systems, the solution is the overlap.